When stable automation meets a moving world, across longer time horizons, the environment does not stay still. It drifts, then lurches. Automation, however, is often built as if tomorrow will resemble yesterday. Automation optimized for stability wins by compressing variance in familiar conditions, but it can break when conditions change, because the same mechanisms that enforce steadiness also suppress early signals of drift. When scaled, this mismatch turns local efficiency into systemic fragility. Edge cases are not merely missed, they are manufactured by the narrowing of what the system is allowed to notice and correct. The result is a pattern of stable case performance paired with catastrophic tail risk failures when the world steps outside the training lane. Begin with the mechanism. Automation seeks repeatability. Define an objective, measure it, and close the loop. Its core constraint is that it can only act on what it can sense, represent, and optimize. Everything else becomes out of scope, not because it is unimportant, but because it is unmeasured or too costly to model. A second constraint follows. The automated controller must choose a limited set of allowable actions, a bounded playbook that keeps behavior predictable. In the short term, these constraints look like virtue. Narrow sensing reduces noise. Limited actions reduce surprises. Metrics create comparability. The trade-off is explicit. Efficiency and stability inside the defined envelope are purchased by reduced adaptability outside it. The system becomes excellent at the average case by paying less attention to the rare case. Incentives then do their quiet work. Builders, operators, and organizations are rewarded for stable dashboards, lower costs, and fewer visible incidents. A feedback loop forms. What is measured is improved. What is improved is trusted. What is trusted is automated further. Trust begets delegation. Delegation reduces human attention. Reduced attention shrinks the chances that someone will notice the early, weak signals of changing conditions. This is not malice. It is consistent optimization under constraints. Over the mid-horizon, conditions shift, inputs change distribution, dependencies evolve, and interactions multiply. The automated system still pushes toward its objective, but now the objective proxies reality less well. Here a second-order effect appears. By enforcing stability, the automation can dampen the small fluctuations that would have served as warnings. When drift begins, the controller corrects it, successfully at first, masking the fact that the underlying world is moving. Stability becomes a kind of veil. Across longer horizons, scale multiplies the consequences of these design choices. When many processes are coupled through shared automation, a local misspecification becomes a correlated error. Edge cases, once isolated, synchronize. The system can move from rare failure to cascade, because the same optimization logic is applied everywhere at once, with the same blind spots. A further trade-off emerges. The more tightly coupled and efficient the system, the less slack it has to absorb surprises. Robustness requires redundancy and diversity. Efficiency tends to remove both. Uncertainty remains central. We rarely know in advance which variable will matter next. A previously irrelevant signal becomes decisive, or a neglected dependency becomes the bottleneck. Under uncertainty, a stability-optimized automation can be rational in the short term, and still be dangerous in the tail. What breaks is not only the code or the machine. What breaks is the assumption that the map of measured reality will remain aligned with the territory of lived reality. This mechanism touches human values because it quietly reallocates responsibility. When a system is stable, responsibility feels diffuse. Outcomes look like the normal operation of the process. When the system fails at the edge, responsibility snaps back into view, often too late to be meaningfully exercised. Automation does not remove governance. It relocates governance into design decisions, metric choices, escalation paths, and the boundaries of what is considered an acceptable exception. Attention is the scarce resource at the center of this. Stability can be purchased by spending attention early on ambiguity, monitoring, anomaly interpretation, and contested definitions of success, or by spending attention late, during incident response and blame allocation. The system will reveal what it values by where it spends attention. If a community's attention is trained only on steady outputs, it may gradually lose the language for exceptions, and with it, the ability to recognize when the environment has changed. So the question becomes less about whether automation is good or bad, and more about what it permits, what it constrains, and what it ignores, especially when the ignored parts are where the future first arrives. A single act of reflection is available. Name one hidden assumption that an automated process relies on for its stability, and place it on a chosen time horizon, short, mid, or long. Then name one tail risk that would emerge if that assumption stops holding. This is not a demand for certainty, it is an invitation to notice how much of normal operation is really a bet on unchanged conditions. Automation can steady the present while narrowing our vision of the possible. Humility begins where the edge cases live,